Hello everyone, my name is Veronica Chipligina, and on behalf of my co-authors who did all the work, I'm going to present our work, Risk of Training Diagnostic Algorithms on Data with Demographic Bias. So our motivation is dataset shift. This is a well-known problem in machine learning where models trained on one dataset show a drop in performance when tested on the other. This can happen for various reasons. For example, different scanners used at acquisition time, but also different annotation policies of the expert, or different distribution of subject characteristics. And in this work, we focus specifically on dataset shift caused by differences in demographics and, in our case, age and sex. So training on biased datasets can easily lead to erroneous predictions at test time. And this is, of course, essential to consider for diagnostic algorithms which will tell if a subject has a certain disease or not. So, for example, several studies have shown that age can be predicted from brain or retinal images. So when we're training a network on a data set of brain or retinal scans in order to recognize a disease, instead of learning the actual disease, the network might be learning the age instead. And unfortunately, creating balanced or unbiased datasets is not trivial in medical imaging, as we all know, especially for datasets that already exist. So in this work, we aim to quantify whether and how such bias is addressed in medical imaging papers which focus on diagnosis of images. We demonstrate the effect of demographic bias on a skin lesion classification dataset, and we show also how it's possible to make the predictions more invariant to potential biases. So the first part of the study, we conducted a survey of different published papers in the MICAI 2018 proceedings, and we looked at whether papers did anything along the lines of demographics of the images. So we included all the papers if they focused on diagnosis or detection of abnormalities. So, for example, segmentation papers were not included. And then for each selected paper, one of the authors quantified the following characteristics. So we looked at the numbers of datasets used and whether they were public or private. We also looked at the number of subjects in the datasets and whether and how demographics were included in the paper or in the algorithm. So in total, we included 65 papers, and only 12 of these actually described some demographics about age or sex. Here you can see the numbers of datasets used. So most papers used only one dataset, and a couple of papers used 2 or 3 or more. And the distribution of whether demographics were provided or discussed, you can see on the right. So most papers do not take this into account. Then we also did a classifier analysis to understand what kind of effect this can have on a classification algorithm. So we took the Isaac skin lesion dataset with a focus on melanoma diagnosis. We chose this dataset because it had age and sex available for most of the subjects, and it was actually quite difficult also to find a public dataset with these characteristics, with the exception of neuroimaging datasets. So here we had the sex and the age available, and the male and female groups were relatively balanced, and then the age was split into 2 subgroups for simplicity. And we used quite a typical setup baseline classifier with an exception V4 network with various segmentations. So these settings were based on recent papers which have relatively good results for this problem. Next to this baseline network, we also used the bias-aware network from the study of Adeli et al. And basically, instead of only predicting the diagnosis, this network has 2 classifier heads, one for the diagnosis and one for predicting these confounding factors, which are, in our case, age and sex. So in order to decrease the predictive power of the encoded features on these demographics, we use a min-max optimization problem where the adversarial loss is a negative squared Pearson correlation coefficient. So if the network predicts the age and sex correctly, there's a correlation between the features and the prediction. So then we give that a penalty and update the encoder weights correspondingly to discourage the network from predicting these characteristics. So here you can see the results. We evaluated the performance of this classifier on the 4 different subgroups, so the male and the female, and then the 2 age subgroups that we split with similar sizes of the groups. And as you can see in the table, the results of the baseline networks are quite unbalanced for the different subgroups. And especially it's surprising for the male and female subgroups because the data set is relatively balanced on that factor. However, using the bias-aware network, the performance gap between the subgroups reduces substantially. However, also overall the performance suffers from this, although it becomes more fair. So here's another visualization of what happens in the background. So here we see this loss, which is a negative correlation. And in the image on the left, when lambda is equal to 0, we see that during training, this correlation decreases. So in other words, actually the correlation between the diagnosis and the confounder increases, which we don't want and is in a bias-free classifier. However, when we increase the lambda, so we use this adversarial loss, we can see that throughout the training process, actually, there's not such a big gap happening anymore. So in other words, this bias-resilient network is effective in reducing the correlation. So in summary, demographics are rarely discussed and used in diagnostic algorithms, at least in the set of papers that we looked at. However, the demographics can influence the final diagnosis task, even if the dataset is relatively balanced. However, we can correct for such potential biases using an adversarial training setting. Of course, in a real situation, we would need to be aware of more of the potential confounding factors in the dataset. So, for example, the type of scanner used, but maybe these are characteristics which are not available in your data. As for some future directions, I think we need better standards for reporting. For example, from computer vision, we know about data sheets and model cards. So we need some more standardized steps of how we describe our data and the demographics in it. And finally, it's important to develop tools to actually assess bias and see how well the algorithms are performing on this issue. And of course, building bias-aware algorithms. Thank you for listening to our talk, and if you have any questions, please contact us in the question hour or through social media or email. Bye-bye.